So this is Mr. Liao. This is the second half of rotations, section 11.3. In the first half, we looked at actually doing rotations, which is the meat of the section. In this video, we're going to be looking at compositions and then ultimately rotational symmetry. So like translations and reflections, a rotation is a rigid motion, which means the lengths and angle measures of any shape are going to be the same from the pre-image to the image. And because the rotation is a rigid motion, the composition theorem guarantees that compositions of rotations and other rigid motions like translations and reflections are also rigid motions. Again, a composition is combining two or more transformations in a single transformation. Example 3a, graph segment RS with the endpoints as shown and its image after the composition. So the first step is to do a reflection in the y-axis and then to do a 90-degree rotation about the origin. So there's segment RS. Let's start with the reflection in the y-axis. So the y-axis rule, a comma b becomes negative a comma b. In other words, just count the units to the line of reflection. So the y-axis goes up and down. R is 1 unit to the right of the y-axis, so R prime has to be 1 unit to the left. S is 2 units to the right of the y-axis, so S prime has got to be 2 units to the left. So its coordinates are -2, -6. So there's the first transformation. It's a reflection across the y-axis. So 90-degree rotation about the origin means the green segment is going to go over there. So the rule is a comma b becomes negative b comma a, or you can do the rotation where you are going to rotate the paper, which is what I'm going to do, and write down the coordinates of r prime and s prime as if the graph were right side up. So here's the new coordinate. Here's r prime. R prime looks like it's at 3, -1. So r double prime is going to be at 3, -1. S prime is at 6, -2, which means S double prime is at 6, -2. Now you turn the paper right side up again and plot down the 2 points that you just wrote down. And there's example 3a. So you do the reflection first, and then you do the rotation. Again, I find it much easier to rotate the paper. 3b, we have another triangle TUV, and now we're going to do a rotation 180 degrees about the origin, and then we're going to do a reflection in the x-axis. There's triangle TUV. Let's start with a 180-degree rotation. So the rule is a comma b becomes negative a comma negative b. If there's a rule you're going to memorize, this is it. Or you can rotate. I'm not going to rotate this time because you could do it on your paper if you wanted. But basically, you would keep the x and y coordinates and you would flip the sign for both. So here are t prime, u prime, and v prime. T prime is at -1, -2. U prime is at -3, -5. V prime is at -6, -3. Now we're going to take the green triangle and do a reflection in the x-axis. So the x-axis is here, which means it's going to end up there somewhere. So the rule again for reflection in the x-axis that a comma b becomes a comma negative b. So in other words, you're going to keep the same x coordinate, but you're going to reverse the sign of the y coordinate. So notice here all the y coordinates for the green shape are negative. Now they're going to be positive. Or you can count how far each point on the triangle is from the line of reflection. So t prime is 2 units below the x-axis, which means t double prime is 2 units above at -1, 2. U prime is 5 units below the x-axis, so u double prime is 5 units above. And v prime is 3 units below the x-axis, which means v double prime is 3 units above. So those are the 3 coordinates after the reflection. So you first did a 180-degree rotation and then a reflection across the x-axis. Rotational symmetry. A figure in the plane is rotational symmetry when the figure can be mapped onto itself by rotation of 180 degrees or less about the center of the figure. In other words, you would spin the figure somewhere between 0 degrees and 180 degrees. And if it ends up exactly where it starts, in other words, you can overlap it with the original shape perfectly, that is called rotational symmetry. The point where the rotation takes place is called the center of symmetry. Now notice the rotation can be either clockwise or counterclockwise. So the figure below has rotational symmetry with 90 or 180 degrees. So notice the 90-degree rotation is exactly the same as the 0 degree. If you were to put these graphs on top of each other, they would match perfectly. The 45 degrees, not so much. Notice that even though it's the same shape, if you tried to put the 45-degree rotation shape on top of the 0, it wouldn't overlap. A point symmetry is when a figure has 180-degree rotational symmetry. In other words, you spin it halfway around, and if it overlaps the original shape perfectly, like here, and 0 and 180, then you have point symmetry. So 4a, does this figure have rotational symmetry? We have a parallelogram. So if you were to rotate it counterclockwise, notice that you only have 180-degree rotational symmetry. You basically have to spin it halfway around, and then it ends up being back in the same orientation as it does when it starts. If you spin it 90 degrees, it won't make it. 4b, we have a regular octagon. Now notice you can spin this and it'll rotate itself 4 times at 45 degrees, 90 degrees, 135 degrees, and 180 degrees. The octagon will map onto itself. Now if you think about it, it could basically be rotated 8 times. It's got 8 different positions where if you rotate it, it would be back to where you started. But again, you only look at rotations under 180. So of those 8, 4 of those are below or equal to 180 degrees. Finally, 4c, we have a trapezoid. A trapezoid has to go all the way around before it maps onto itself again. So the trapezoid does not have rotational symmetry. So this was pretty long. If you have any questions, you can ask me, but really focus on the rules for rotation. If you don't remember the rules, that's fine. Remember, you can always rotate the paper.